Hello, viewers. Get started once we get a few more people watching. Dum-de-dum-de-dum. Hello again. Hello. It's Buenos Dias, right? It's not Buenos Tardes yet. How was the octopus movie? Um, it was really good and really sad. I definitely cried at the end, and I would recommend it to everyone. I also saw Tenet this weekend, and I would recommend that to everyone as well. Actually, I thought Tenet was going to make no sense um, compared to some of Christopher Nolan's other movies. Don't make a lot of sense to me. Like in particular, Inception. I think Inception just doesn't make sense. Um, so I went into it. Tardis is afternoon, I believe. Yeah, and we're still in the AM. Um, and so, anyways, I went into Tenet expecting for it to make no sense, and I was actually surprised that it made a lot of sense. And um, I've read a book that has a similar concept in it. Um, there's a book called what is it? I'm gonna go grab it from my bookshelf. Yeah, there's a book called Hyperion, which discusses the concept of reversing entropy. So if you somehow reverse the entropy of an object, you basically send it backwards in time, because instead of its entropy increasing as time goes on, it decreases as time goes on. So Tenet, so in the book Hyperion, they are basically their humanity in the future has sent things back in time to the present, and a similar thing is happening in Tenet, almost exactly, but it's like James Bond meets Hyperion, kind of is how I would describe it. Um, yeah, and I see someone loves the book, so I will definitely talk to you about that in the Zoom room after today's lesson. Okay, so what are we going to talk about today? We are going to talk about inclined planes. Okay, and these are an important thing in physics. Inclined planes are really important in physics. Just as an example of a lot of the different concepts. So, how does an inclined plane work? Well, we've got a plane, And the plane is described by the angle that it makes with the horizontal, angle theta. Okay. And then it has a box on it. And so the thing about the box has a mass m, and there is friction present. So there's some coefficient of kinetic friction. We're going to take friction to be kinetic, so that means that the box is actually sliding either up or down the incline. But we have to be a little bit careful, because if the box is sliding up the incline, then friction is going to point downwards, down parallel to the incline, but downwards. If the box is sliding up the incline, or down the incline, then friction is going to point up. So friction is an oppositional force. So whichever way the box is sliding, friction is going to point the opposite of that. Okay? So anyways, let's go ahead and pick some specific numbers. So let's suppose that the angle is 65 degrees. Let's suppose that the box has a mass of 2 kilograms. And let's suppose that the coefficient of kinetic friction is 0.3. Okay? So now what I'm going to do is I'm going to draw a free body diagram of the forces on the box. Okay, so when I do a free body diagram, I just represent it as a dot. The box is a dot. Oh, and I'm going to assume motion down the incline. I will assume motion down the incline. Okay? All right. So, meow. Cat just walked by. So what are the forces we have? We have the normal force, which points perpendicular to the incline. We have the weight force, which goes downward, and the weight force would be 2 kilograms times 10 meters per second squared, so that would be 20 newtons. And then because I'm assuming that the motion is down the incline, friction is going to point up the incline. And it's going to be kinetic friction. Okay? Now, there's a couple of things about drawing the free body diagram like this that makes it a little bit cumbersome. Okay? So the first thing is that the acceleration is diagonal. That's annoying because we have an x component to the acceleration and a y component to the acceleration. Okay? The other thing that's annoying is we have normal force and friction are also diagonal, which means that, you know, we'd have an x component and a y component to friction. We have an x component and a y component to normal. If a force is vertical, it only has a y component. If a force is horizontal, it only has an x component. So basically, we want to try to set up our problem by you set up the problem by, you're going to make it as easy as possible by making as many things horizontal and vertical as possible. Okay? So what I'm going to do is I'm going to take this picture and I'm going to rotate it by 65 degrees. Notice how if I do that, which way does friction and normal point? Well, friction points horizontally. Normal points vertically. And then the acceleration is going to be side to side. So see how that simplifies the problem? Okay. Now, here's the interesting thing. If I rotated this paper by 65 degrees to make the plane flat, what happened to the weight force? The weight force started out vertical, But then, because I rotated the whole paper 65 degrees, okay, then that means that this angle, whoa, this I did not draw this very perpendicular. That means that this angle right here is 65 degrees. Do you guys see why that is? I rotated the paper 65 degrees. So all of these arrows got rotated by 65 degrees. Okay? All right. So now I'm going to call this the positive x direction. All right? So now what I'm going to do is I'm going to take the diagonal force and I'm going to break it up into components. So this component is going to be opposite the angle. So that's 20 sine of 65. Okay? So I have 20 times the sine of 65, which is 18.1 newtons. So that is 18.1 newtons. And then that, the vertical component of the 20 newtons is going to be 20 times cosine of 65, which is 8.5 newtons. Okay? So that's the first step, is to just kind of reorient yourself so that the motion is horizontal. So we have as many forces are vertical and horizontal as possible. Okay? Now what we do is I'm going to redraw the free body diagram, but this time I'm going to write the diagonal force as being a vertical force and a horizontal force. So I've got normal force going this way. Okay. I've got 8.5 newtons going down. I've got 18.1 newtons going this way. And I've got friction going that way. Okay? Okay. All right? So that's how that works. And so notice I wrote the 20 Newton force as two forces. Okay? Now here's the thing. This box is sliding side to side along the incline. Okay? It's not sliding up and down. It's going side to side. So because the box is moving side to side, we have to have the upward forces equal the downward forces. Why is that? Because if the upward forces were not equal to the downward forces, then the box would be jumping up off the incline or squishing into the incline. Okay? So that means that the normal force has to be 8.5 newtons. Now, if we know the normal force, then we can calculate kinetic friction. Okay? Because as we learned in the last lesson, then I've been thinking too much about tenet. As we learned in the next lesson, I'm entropy reversed, I guess. Kinetic friction is coefficient of kinetic friction times normal. Okay? So that would be 0.3 times the normal force, which is 8.5. So that's going to be 25.5. 2.6 newtons is going to be friction. Let me double check that I did that mental math correctly. Yeah. So this is 2.6 newtons. So now we actually, and by the way, this is obviously not drawn to scale because I haven't drawn the arrows' actual lengths to represent their numbers. Like this should be the longest arrow, that should be a really short arrow. These two arrows should be in between. So now I write a Newton's second law equation in the x direction, which is this direction. So the net force in the x direction is equal to mass times the x acceleration. The net force in the x direction, well, I've got 18.1 newtons to the left, and I've got 2.6 newtons to the right. So I have 18.1 minus 2.6 as my net force. I'm defining leftward to be positive for this problem. Then I have mass is 2 kilograms times the acceleration. So 18.1 minus 2.6 is 15.5 equals 2a. Divide both sides by 2. I get 7.8 meters per second squared is the acceleration down the incline. So once we calculate the acceleration, we can then calculate things like how fast is it going to be going, how much time is it going to take to traverse the incline, things of that nature. Okay? So if you were in my AP Physics 1 class, we went over the inclined plane with friction. If you were in my IB Physics SL class, IB Physics SL, then I think we did the inclined plane but no friction. So this is how you would incorporate friction. Okay? Let's throw another wrench into this. What if we add an additional force? So let's do an inclined plane again. Okay. So example. What if I have an inclined plane that makes an angle of 20 degrees with the horizontal? There is a block there is a block that is, let's make it 3 kilograms, okay, acting on the, and then the coefficient of kinetic friction is going to be 0.1, and someone is pushing horizontally on this box, okay, with a 75 Newton force. Okay? Now, I'm going to assume that this 75 newtons is in, well, actually, okay. I suspect that 75 newtons is going to be enough to make the block move up the incline, not down the incline. Okay? I'll show you how to do this. I'll show you how to determine whether it's going to move up or not in just a second. So let's draw a free body diagram. So we've got this horizontal 75 Newton force. We've got 30 newtons downward. That's the weight force. We've got the normal force, which is perpendicular to the incline. And we also have friction. I'm not sure which way friction is going to point because I don't know which direction this box is going to go. So I'm just going to leave everything. I'm just going to leave out friction. Okay. Now I'm going to rotate the paper by 20 degrees. Okay. So that this is now level. Okay. So if I rotate the paper by 20 degrees, then this arrow is rotating to the left 20 degrees, and this arrow is rotating down 20 degrees. So I go like this. So that means that this arrow got rotated down by 20 degrees from where it was. So that means that this angle right here has to be 20 degrees. And the 30 newtons got rotated to the left 20 degrees from where it was. So this is 20 degrees. So there's a little geometry for you. All right? Now, anytime you have a diagonal force, what you want to do is you want to take it and break it up into components. So if I have a 75 Newton force and this is 20 degrees, that's going to be 75 sine of theta. 75 sine of 20 is 25.7 newtons. This is going to be 75 cosine of 20, which is 70.5 newtons. Okay. Now let's look at the 30 Newton force is going down like this. It's a right angle. This is 20 degrees. This is 30 newtons is the hypotenuse. So to get the vertical part is going to be 30 times cosine of 20. 28.2 newtons. This is going to be 30 times sine of 20, which is going to be 10.3 newtons. Okay. So now I'm going to redraw my free body diagram with the diagonal forces drawn as two forces, one vertical and one horizontal. Okay, so I still have my normal force. Rotate this all the way so that true. Okay, I still have my normal force. I've got 70.5 newtons going this way and 25.7 going this way. All right, that comes from this force right here. And then from this force, I have 28.2 newtons going down, and I have 10.3 going to the left. Okay, so what I can see here is that my rightward force is a lot bigger than my leftward force. So that means that this box is going to accelerate to the right, which is up the incline. Now, if it is accelerating to the right up the incline, then that means that friction has to point to the left. Okay? So friction actually pointed in this direction here. So I waited to put friction in until I could see whether it's going to go up or down. Okay? All right. So what do we do now? Well, we are going to do Newton's second law in the y direction. Now, the y acceleration is 0. Why? Because the y acceleration is 0 because the box isn't jumping off the incline or getting crushed into the incline. So what that means is that the net force in the y direction is the upward force, which is normal, minus the two downward forces, so minus 28.2 minus 25.7. And those have to equal 0. They have to combine to 0. Because if they didn't, the box would be accelerating in the up and down direction, which is not. We know it's sliding along the incline. It's not jumping along the incline. Okay? So, we have 53.9 newtons is the normal force. So this is 53.9. Now, what the normal force allows us to do is then calculate kinetic friction. So then kinetic friction is mu sub k times normal. So that would be 0.1 times 53.9 which is 5.4 newtons. So that means this is 5.4 newtons. Okay? So now I know the value for all of my forces. Okay? So now I can calculate the acceleration. So I can go to Newton's second law in the x direction, because recall the block is moving along the horizontal direction, which is the x direction. That equals ma. I'm going to choose this to be the positive direction, rightward to be the positive direction, because the block actually moves to the right. So I've got 70.5 newtons going to the right. I've got 10.3 going to the left. And I've got 5.4 going. Can't see that, can you? I've got 5.4 going to the left. And that equals ma, so 3a. Can solve for the acceleration. 70.5 minus 10.3 minus 5.4 divided by 3 is 18.3 meters per second squared. Okay? So let's go over the steps to solving these problems. Okay? The first step is to draw your free body diagram. Okay? Draw your free body diagram. Then I would recommend rotate your paper so that the incline is actually horizontal. Okay? Then what you're going to do is write any diagonal forces as a vertical and horizontal force. Using trigonometry, okay? Then what you want to do is you want to after you have done that, you want to use the fact that the block does not accelerate perpendicular to the incline to deduce that the net force in the y direction is 0, and you can get the normal force by solving that equation. So you can determine what the normal force is. Then, once you know what the normal force is, you calculate what the friction force is, because the frictional force is mu sub k times normal. And then, once you know what friction is, you use the horizontal Newton's second law, so the net force in the x direction equals ma, and you can solve for the acceleration. Okay? So you can see I went through all these steps in this example. I wrote the free body diagram. I rotated the paper. I then identified this force and that force as being diagonal, so I broke them up into components, and I redrew the free body diagram with all the forces being vertical or horizontal. Then I used the net force in the y direction as 0 to get the normal force. Then I calculated friction, and then I calculated the acceleration. So those are the steps. Let's just talk intuitively for a second about this. This is a horizontal force, horizontal applied force. What is its effect? Well, you can think about this. This force is partially pushing the block into the incline and partially pushing the block along the incline. In fact, this 75 Newton force pushes the block into the incline with 25.7 newtons and along the incline with 70.5 newtons. Okay? So this portion of the force, the 25.7, is going to increase the normal force, which is then going to increase friction. All right? So, applying this force can actually reduce the acceleration by it kind of depends on what the angle is. Okay, if the angle is super steep, then what applying a horizontal force will do is it'll increase the normal force more than it increases the force along the incline, and so you'll actually, even though you're pushing on the block, it's not going to accelerate as much. So it kind of depends on the situation. All right. So that's my lesson for today. And so I will see you in the Zoom room. All right? Ta-ta for now.